that this session is being recorded, and what I will do is when we finish, then I will send you a link on Moodle, and also you'll be able to on your MS Teams find the link so that you can maybe go through the problems that we are going to discuss in case you have any more challenges or problems with the work we're going to cover. Right, so I'm going to switch off the video. You'll only be able to hear my voice, and then I'm going to share my screen. I just need to take you to what we covered last time and then show you what we need to cover today. So last time we did tutorial 8. We used it as a revision. I just need to scroll down and show you the tutorial. Excuse me. Right, okay, this is the tutorial we did last time. So we, as part of the revision, we completed calculating support reactions for question 1, question 2, and question 5. And what we need to do now is to complete question 3 and 4, but I'm going to start with question 4, and I'll leave the one with inclined loads for later, so that maybe by then most students would have joined us. So what I'm going to ask you to do, like last time, obviously you need to have a piece of paper, you need a calculator, so that you can work through the problems as we do them in class. So this is the problem we're doing, this beam with 2 overhangs or 2 cantilevers. So just take note of this one, because obviously I'll have to use a document camera to show you what I'm doing. Right, so just take note of this problem. Okay. Right, so I've got it in front of you, where I'll be doing the actual calculations. Right, so what we need to do here is to calculate the support reaction. Okay, I think somebody is trying to talk. I'm listening. If you have any questions, do you want to say something? Okay, nothing. Okay, I'll continue. So to calculate the support reaction at node B, the vertical reaction at node B, I'm going to use or apply the second condition of equilibrium. We said the second condition of equilibrium is sum of the moments equals to 0. So I'm gonna take sum of the moments at node E equals to 0. So let me write a statement for that. So we're saying for VB, let sum of the moments at node E equals to 0. In terms of the sign convention we are using, we said clockwise moment is positive, anti-clockwise moment is negative. So I'm going to assume that VB is going up. So if VB is assumed to go up, then it is going to cause clockwise rotation about node E. And then I have a plus sign. Right. VB is the unknown. It is the unknown component. The lever arm for VB is 1,5 plus 2,5 plus 1. That's the lever arm for VB. So we've got 6 VB, and VB is causing clockwise rotation about node node E. So let me just check the dimensions and make sure that the dimensions are correctly here. So it's actually not, sorry, it's not 6, it is 5. My apologies. So it's 5 VB, right? So that's 4 and that's 1. Okay, not 2. 2 is on the other side. So we've got 5 VB. And then you need to then ask yourself this question. Do we have any other load that is causing clockwise rotation about node E? Okay, definitely not 7,5 kilonewton per meter, not 10. It can't be that 5 kilonewton per meter. And it cannot be the portion of the 10 kilonewton per meter UDL on the left-hand side of node E. We do have a load, a UDL between node E and F. We have a UDL that is causing clockwise rotation about node E. So I'm going to give it a plus. The UDL is 10 kilonewton per meter. At 10 kilonewton per meter is a uniformly distributed load. We need to change it to a force. So a force, or the weight of the load, is 10 kilonewton per meter times 3 meters. Then you get a 30. Okay, but I'll still write it here as 10 over a distance of 3 meters. So the 10 is 10 kilonewton per meter and the 3 is 3 meters. This is now a force. 10 times 3 is a force. We need to get the moment as a result of that load. So that force of 30 kilonewton is acting somewhere here. And then the lever arm for that force is then 3 divided by 2. 3 divided by 2 is 1,5. The unit there is meters. Right, so what we're saying is this is a force, and then this is a lever arm, the perpendicular distance. Right, so I'm done with that part. So let me just highlight what we've done now. So we've got that taken care of. We've got a VB taken care of. Now we have loads that are going in the anti-clockwise direction about node E. So anti-clockwise is minus. So we've got minus there. So the first one, let me start off with the point load. We've got a point load of 10 kilonewton. The lever arm for the point load is 2,5 plus 1. Okay, 2,5 plus 1. So for the point load, we've got 3,5. And then minus, then we have this UTL, that small portion of 10 kilonewton per meter over a distance of 1 meter. So we've got 10 kilonewton per meter over a distance of 1 meter. So this is now a force. That force is acting somewhere there at the center of node D and E. Okay, so then the lever arm is 0,5. Then the next load is 5 kilonewton per meter. Kilonewton per meter is
sorry, sir.
Yes, I'm listening. Sorry.
Can you please explain to me why can't you just do the 10 times 4 times 1 instead of just doing the times 1.5? Why is it like you have to break it apart? Is there any explanation why?
Yes, there is an explanation for that. Right. If this is a support, right? We've got a point here where part of the 10 kilonewton per meter is causing clockwise rotation about node E, and the other part is causing anti-clockwise rotation about node E. Okay, right. So what I'm going to do, let me get a red. Also, I've got a blue one here. So this is where we have node E. So when we did the first part, we said, right, for VB, we're assuming that VB is going up. So VB is going to cause clockwise rotation about node E. Going to cause clockwise rotation about node E. And then we said part of 10 kilonewton per meter is causing clockwise rotation, and the other part is causing anti-clockwise rotation. So then the part that is causing clockwise rotation about node E is this one, there on the term. 10 times 3 being a force, and then the lever arm for that force is 3 divided by 2. Right, so that one is going clockwise. This one is also going clockwise about node E. And then now we have forces that are going anti-clockwise about node E. And then we said the first one is the point load. Okay. And the lever arm for the 10 kilonewton point load is 3,5. And then the second one is that portion of 10 kilonewton per meter. Only that portion of 10 kilonewton per meter, which is causing anti-clockwise rotation about node E. So that is 10 times 1, which is now a force. And then the lever arm for that force is 1 divided by 2. So that's the lever arm there. And then now we have the moment. I don't know if that answers your question. Sorry, I'm not sure who was talking. Sorry.
No, it's so basically what you're trying to say is well, we know the directions of like okay about the shear force or of those graphs that we saw in the notes. Is you saying that was going to help us to identify where the line is going to go? But that's what
Yeah.
this is the purpose of it. Is that it?
No. No. It's not the purpose of that. Basically, it's sticking to what the assumption we made. What I wrote here is this: for VP, for us to work out VP, if we apply the second condition of equilibrium. So what are we going to do? What procedure are we going to use? So we're going to say let sum of the moments at node E equals to 0. And then we move on to the sign convention we're going to use. Then we said moments that are going in the clockwise direction, we're going to give them a plus, and then moments that are going in the anti-clockwise direction, we're going to give them a minus. So I'm just sticking to the procedure we're using. We adopted to work out the vertical reaction at node B. We haven't come to the shear force diagram. We will after this one, and then you will once we have the support reactions, then I will show you how we're gonna go about drawing the shear force diagrams. I don't know if other students are having a problem. I mean, are you?
No. One more thing. Last question is
Yes.
if I do it the way I said it, do it like 10 times 4 times 1, will the answer differ from what you are doing?
Okay.
Will my answer differ to yours?
You want to say, but we're taking moments about which point?
The one you just showed me, the 10 kilonewtons, because when we did that stuff, calculate the momentum at the supports, I didn't calculate using your method. I calculated by just timesing it by 10 times 4 times 1.
Yeah, okay. So in your case, you're saying 10 kilonewton per meter times 4. Okay,
yes.
4 is 1 plus 3. So you have a force there of 40 kilonewton. Then your lever arm is different because your force is at the center of node D and F, which is there. And that's exactly the same thing.
Exactly the same. Okay.
Yeah, it's exactly the same thing. Yeah, yeah.
All right. So thank you.
Okay, but sorry, Jordan.
Yes.
Right. What I want you to think about when you have time is the fact that basically I'm splitting the load. It can be you can split the load because the portion of 10 kilonewton per meter on the right hand side of node E is causing clockwise rotation. Then the other portion of 10 kilonewton per meter on the left hand side is causing anti-clockwise rotation.
All right, I understand that.
Okay.
I understand.
Okay, right. Thanks.
Sorry, sir. Sorry, sir.
Yes, I'm listening.
Whilst the other student was talking, I heard you say that if he uses 10 times 4 times 4 over 2, that the answer will be the same as if you're using your method. But then if you put 10 times 4 times 4 over 2 into a calculator, the answer is 80 kilonewtons. Whilst if we're using this method with the one which you taught, you're teaching, the 10 times 3 times 3 over 2 is equal to 45 kilonewtons, and the 10 times 1 over 2, and its minus is 40 kilonewtons. So the whole portion exerts 40 kilonewtons. So I don't understand, how can both methods be right?
You need to compare it to the overall. Oh, so sorry, you can speak actually, I'm sorry.
You said put the calculator 10 times 4 times 1, not 2. The different from the support to the center, which is, so it's the middle of that thing. 4 divided by 2 is the middle. The difference between the support to the middle is 1. So you times it, so it is the same.
Sorry, you're saying the distance is 1?
Yes. The entire size of the 10 kilonewton box is 4. The support is 1 meter away from the D, and from the center to the support is 1 meter.
Yeah, because his force is there now.
So it's divided by, so it's 10 times 4 times 1. So it's 40. So it does equal.
Excuse me, unfortunately, I don't understand that
fine.
method, but
Mr.
cool.
Mashaba, Mr. Mashaba, sorry if you do, oh, sorry, not Mr. Mashaba, my apologies. It's Makazi. What I will do is, sorry, Jordan, I think you submitted yours as far as I remember. What I can do is, if you don't mind, I can actually show him when we finish. Is that okay?
Cool, sir, no problem.
Okay, I'll show you, Makazi. Sorry to worry you, but I'll show you how it's done it.
Okay, sir.
Okay, I'll show you, Makazi. Okay, right. Okay, students, I think let's continue. Right. So I just need to make sure that okay. So we've done that part. Now I'm going to move on to the 5 kilonewton per meter uniformly distributed load. Right. So as far as that load is concerned, this UDL, it is causing anti-clockwise rotation about node E. So I'm going to give it a minus sign. Right. Then the UDL is 5 over a distance of 2,5. and then you have a force now. So this is now a force. So we have a force. Right now we need to determine the lever arm for that force. So the lever arm for the force is half of 2,5, which is 1,25, and then plus 1. Okay, the force is there. So the lever arm is 2,25. And then let's move on to the last load, 7,5 kilonewton per meter. That load is also causing anti-clockwise rotation about node E. Hence, I'm going to give it minus. So we've got minus 7,5 acting over a distance of 3,5. Okay, that's 2 plus 1,5. So we've got 3,5. Sorry, I'm running out of space, and then so far we have a force, and then the lever arm is 1 plus 2,5 plus 1,5, and then let's be a little bit careful here. That load is acting on the left of node B. So what you can do, if you like, you just say 3,5 divided by 2 plus 2,5 plus 1. And what do you get for that? Okay, that's 7,5 times 3,5 is acting somewhere here to the left of node B. So 3,5 divided by 2, right? And then plus 2,5 plus 1. So you should get 5,25. That's the lever arm. Okay, you're gonna get 5,25. Right, and then when we're done, that equals to 0. Don't forget, okay, I'm running out of space, but this whole thing should be equal to 0. Because so far, what we've got here is the sum of the moments at dot E, and then that equals to 0. And then the question is, what is VP? So please, can you help me calculate what VP is?
How about 56.5625 kilonewtons going up? Oh no, excuse me. I read I read the other answer. Our VP is 32.1875 kilonewtons.
Okay, let me just check something here. You said saying 32. Okay, right. Are you getting 32, comma whatever, using the numbers that are showing on the screen, or you just giving us the value from your homework?
Using the numbers that are showing from the screen, which are using.
Okay, thanks, Makazi. Anyone who's agreeing with that answer before we write it down?
Yes, he's correct, sir.
Okay, thank you very much. Right, so you said 32, comma?
1875.
Okay, let's say 32. Okay, excellent, right. Please, that up is very important. So 32,19 kilonewton up. Right, and then now we're going to say for VE, let sum of the moments at node B equals to 0. Okay, right, then I'm going to assume that V is going up. So if V is going up, and we're taking moments about node B, so we're going to give it a minus sign, as you can see there, right? We're going to give it a minus sign. So that's 5VE minus, then we have, I just need to, also adjust this because my apologies. Okay, right, so we've done this one, VE times the lever arm. That force there, this one is causing anti-clockwise rotation about node B. Okay, so minus 7,5 over a distance of 2 meters times the lever arm is 1. Then we have moments that are going in the clockwise direction. So that's plus. So that's 7,5. Okay. Is the first one I'm going to look at. So it's 7,5 over a distance of 1,5 meters, and then times the lever arm. Okay, so we need to work out the lever arm for that. Okay, so what is 1,5 divided by 2? So you've got 0.75. The next one is the point load. So plus 10 times the lever arm for the point load is 1,5. Okay, followed by the UDL of 5 kilonewton per meter. So plus 5 over a distance of 2,5. And then we have a force acting somewhere here. Now, what is the lever arm for that force? So 2,5 basically divided by 2 and then plus 1,5. So you get 2,75. And then the last one is 10 kilonewton per meter. So plus 10 over a distance of 4 meters, right? And then the lever arm for the 10 kilonewton per meter UDL is 2 meter plus 2,5 plus 1,5. So you get 6. This equals to 0. And then please, can somebody work out VE for us? Okay, sorry, I think I lost the connection on my side. Can you hear me now?
Yes, sir.
Okay, excellent. Thank you very much. So what is VE?
56,56.
Okay, very good. So 56,56 kilonewton going up, right? So don't forget the direction. Okay, what is the sum? What is the sum of vertical reactions equal to? Anyone, please? Sum of vertical reaction. Here, these two numbers. On my side, I'm getting 88,75 kilonewton up. Then what you need to do now is to check it against the sum of the forces in the y direction. So there is 7,5 times 3,5 and then plus 10 plus 5 times 2,5 plus 10 times 4. So what do you get? So 7,5 times 3,5 plus 10 plus 5 times 2,5 plus 10 times 4. What do you get? Anyone, please? Anyone?
88,7.
Okay. All right. Right. Thank you very much. And then basically it's okay. So this is how you're going to check your support reactions. This is how you're going to calculate your support reactions, right? So what we need to do now is to move on to the last one, this one, okay? The one with inclined forces. So, and I'm gonna ask you again to note this question down. Okay. I hope you finished. So I managed to finish on my side. I'm gonna ask for a big favor. So the way I'm gonna do it is this: that 40 kilonewton inclined load, with your permission, I'm gonna break it down into vertical and horizontal component right away. So I'm not gonna put it here as an inclined force. Similarly, a 25 kilonewton inclined point load, I'm going to, obviously with your permission, ask to just write it down as a vertical and horizontal component. Okay, so the first one that I'm going to ask you to help me with is the vertical component of a 40 kilonewton. So the vertical component of that inclined 40 kilonewton point load is 40 sine 45. So then the question is, what do you get? So I'm just listening. You can just unmute your mic and then give us the answer and then mute your mic. So what is 40 sine 45?
20
Oh,
it's 28.284.
Okay, so you're saying 28,28 kilonewton. So let me open this. So it's 28,28 kilonewton. Okay, and then thank you very much. And then what is the horizontal component of that force? So what is 40 cos 45? Then you should get exactly the same thing. Okay. Right, let's move on to the 25 kilonewton inclined point load. So the vertical component of this inclined force is 25 sine 30. So what do you get? Sorry, Menier?
12.5.
Okay, thanks. 12.5 kilonewton. And then the horizontal component, 25 cos 30. 21 comma 6. Let me just 65 in fact. 5 kilonewton. Everybody is happy so far. Okay, thanks. Right, and then let's start with the what I forgot to write here. My apologies. This is note A. At note B, note C, note D, note E, note F. Okay, same thing we did previous. For VB, let sum of the moments at node F equals to 0. And I'm gonna take clockwise as positive, anti-clockwise as negative. Okay, and then what is the lever arm? I would like to get these answers from you. This is the last one we're doing now. So please, I would like to get these answers from you. So if you're ready to give the answer, you can just unmute your mic and then tell me what the answer is. Right. So for VP, what is the lever arm for VP? I'm listening. Okay.
10.5.
Thank you. 10.5 VP. 10.5 VP is causing clockwise rotation about node F. So we've got a 10.5 VP. And then the question I want to ask now is, do we have any other force that is causing clockwise rotation about node F? The answer to that is no. So the rest are going anti-clockwise. We're taking moments about node F, and then we have a force of 12,5. So 12,5, the lever arm for 12,5 is 1,5. This one is causing anti-clockwise rotation about node F. The next one, okay, let me do that point load. We've got minus 28,28. The lever arm for 28,28 is what? Anyone who wants to help us with that? What is the lever arm for 28,28? You said 8.5. Right? Okay, right. Then we're going to move on to the 18 kilonewton per meter uniformly distributed load. There's 18 there over a distance of, then that's the distance there. Okay, so 18 times 5 times, what is the lever arm for at UTL? We're taking moments about node F.
8.75.
No, we're taking moments about node F. What is the lever arm for this UTL? We're taking moments about node F. What is the lever arm for that UTL?
2.5.
2.5.
Is 2 point?
2.5.
Okay, so it's 2.5. So the 3,5 plus 1,5 divided by 2. Right, and then followed by the 10 kilonewton per meter over a distance of 7,5. Now the question is, what is the lever arm for this force? What is the lever arm for that force?
No, that is 8.75.
8.75. Okay, thank you very much. And this was the last one, so equals to 0. So what is VP equals to? Sorry, sir. Sorry, who was talking?
I got 108.61.
Thank you very much. But your answer is incomplete.
Kilonewtons upwards.
Okay, 108.61 kilonewton, and then the direction
Upward.
say up.
Yes. Said upwards.
Okay, thanks. Okay, my apologies. Right, and then for VF, what are we going to do? So we're going to say for VF, let sum of the moments at node B equals to 0. So we're going to stick to the same sign convention. Right, so we're taking moments about node B. We know the lever arm for VF. So we start with minus 10,5 VF. Okay, so this is an anti-clockwise moment if we're taking moments about node B. Be careful, we have this portion of 10 kilonewton per meter causing anti-clockwise rotation about node B. So minus, and there's 10 over a distance of 2 meters, and then the lever arm is 1. So if you like, you can just write it as 10 times 2 squared over 2. Right, then the rest are causing clockwise. So there's a plus there. The first load is this one, 28,28. The lever arm for 28,28 is 2 meters, followed by that point load there of 12,5. The lever arm for 12.5 is 9. Okay, and then plus the first UDL I'm going to look at is the portion of 10 kilonewton per meter UDL on the right hand side of node B. Okay, that portion there. So we've got 10 acting over a distance of 5,5, and then the lever arm for this 10 kilonewton per meter is obviously 5,5 divided by 2. Right, and then we've got plus, okay, this one now, the 18 kilonewton per meter. So we've got 18 over a distance of, so that 18 is along node D and F, between node D and F. So it's along a distance of 3,5 plus 1,5. Right, so if you like, so we're taking moments about node B. So what we can't just write it as what I wanted to write it as. In fact, don't mind. But we're taking moments about node B, so I can't use that that small equation I was thinking about. Anyway, so what is the lever arm for this force now? What is the lever arm for the force? What is the lever arm for this force? Force here, we're taking moments about node B, don't forget. So the force is there. So the question is, what is the lever arm? So what you need to do is to say, right, 3,5 plus 1,5. Okay, get the answer for that, divide by 2. So you add 3,5 and then you add 2, and then you should get 8 for that. So that's going to be 8, right, equals to 0. So the question is, what is VB equals to? Anyone? So what I'm asking you to do is to get your calculator, do the numbers, and then tell me what the answer you're getting. Okay, while you're doing that, I'm gonna make just one small correction here. That's supposed to be F. This one is not working, so. Okay, that's supposed to be F. Okay, what is VF?
I got 97,173 kilonewtons.
Up. Okay, that's
Up.
F there. Yes, and that's F. My apologies for that. Okay, but it doesn't affect the calculation. It is VF we're calculating. So, what is the sum of vertical reactions? Anyone? So, what you get if you add VB and VF? That's the question I'm asking. What do you get? Okay, I'm getting 205.7. Thanks. Going up. Okay, so the same student, please can you then work out the sum of the forces in the y direction for us? So what is 28.28 plus 12.5 plus 18 times 5 plus 10 times 7.5? What do you get?
$205.78.
0.78 kilonewton going down. This is sum of the forces in the y direction externally applied, right? So therefore we're okay vertically. Now,
Sorry, sir.
how do you work out the HB? So sorry, so somebody was talking.
Yes, sir. Sorry, sir.
Yes, I'm listening, sir.
Yes, sir. Like according to my calculations, sir, like for F, I got 104.32, and for B, I got 101.46. And at the end, it's still balancing like the sum of the verticals. Like, yeah, I'm still getting 205 at the end.
Okay, there's a systematic error there. I think on your side, you're welcome. Did you submit that the assignment?
Yes, sir.
Okay. What you can do is I just drop me an email. Then I'll look on your assignment to see what where you made a mistake.
Okay, sir. Thank you, sir.
Okay, thanks. Right. So where are we? Right. HB. So let's discuss HB. So I've got 28.28 going east. This is an externally applied force. You remember the horizontal component of the force that was inclined at node C. So we've got 28.28 going east. And we also have 21.65 kilonewton west. So it's clear for us, it is clear to us to see that when you look at these two forces, you're going to end up with a resultant of a certain number going east, right? So then the question is, what is that number? What is 28.28 kilonewton minus 21.65? What do you get?
$6.63.
Yes, thank you. 6.63. 6.63 is the resultant of the two components, right? 6.63 is going east. So as far as HB is concerned, we need equal but opposite direction. Okay, that's basically what we need. So we need to move on to shear force diagram. Before we proceed, I need to ask you something. Have you discussed with your lecturers, for those of you that have practicals, when you're going to come to campus to do the practicals? Because I need to determine how I can issue the textbook to you.
No, sir. Actually, sir, I was going to ask the question after class, and I sent the lecture for what you call this, for civil engineering materials, an email asking about that particular subject, and she said that campus is closed, so then we must wait until campus opens, and then you will duly inform us with regards to the practical date.
Okay, but then the practical time shown in the timetable.
Yes, there is a practical time on the timetable.
Okay, is it which day of the week?
Hold a sec. Okay, I'm going to check now.
Oh, okay, no, it's fine. Whenever you get time, please let me know, because what I'm trying to do is to, when you come for your practical, whichever practical, then I'll just come one time and then give you the textbook. And then those who are not doing the subjects, I don't know if there's any subject with practicals, then obviously we'll have to make special arrangements for that.
Sorry, sir.
Yes.
On my timetable, this one I have, I don't know whether it's updated or not. There is no practical time for structural mechanics, STM. The only practical time there is here is water, hydraulics, civil engineering materials, and yeah, it's water, and yeah, it's only those two.
Okay, when is civil engineering materials practical? Is it a Friday, Monday, Tuesday?
It's Tuesday and Thursday.
Okay, what I'm gonna try and do is on Tuesday, and when you come for, whenever you come for your first practical, then I'll try and actually come downstairs to issue the books. That's what I'm gonna try and actually do.
Okay, sir.
Okay, right, and then right. So as far as the revision for support reactions, then we are done. So then let's go back. Students who registered late or missed the first two lectures. Right, so just make sure that you complete the first part of this tutorial. We've done it in class. When you get time, please make sure that you are able to calculate the support reactions for all these problems, especially the last one. This is the last one. You can see the last one is a little bit, the problem is a little bit busy. So make sure you can do this one. What I'll do is, I think we need to then proceed with the shear force diagrams. Before we do that, let's go to a relevant theory. So for now, I'm going to use your study notes, not your textbook. So on page 11 of your study notes, you have, where's page 11? You have the sign convention for shear. So this is a sign convention for shear. Now, what is it saying? Okay, so we're on page 11. Positive shear is when the algebraic sum of the forces to the left of a point is upward. Right, so let's look at this one first. Right, so this is the section. We're cutting through a beam. If the algebraic sum of the forces to the left is up, we will take that as positive shear. Okay, that's all you need to know, because the rest you just need to use equilibrium or apply the laws of equilibrium. So on
Can
the
you just
left,
explain that again?
if the algebraic sum of the forces to the left of the section go up, that is taken as positive shear. I'll give you, let me try and give you a nice example. I'll do it just now. Right, so just give me 1 second. I want to use Microsoft Word. Yes. So what do we mean by this? Let's say you have a beam. So this is a beam. So you're gonna go to the structure and then you consider a section. So this is the section that I'm considering. So that's where I'm gonna cut the section. Okay, let me move it slightly. So obviously there's a support on the left, support on the right. Let me just show the support maybe just to make our life easy. So there's a support there on the left. There's another support on the right hand side. So here's a simple supported beam. We cut a section through here, any point. Here's the point. That's where we cut into section. Now, what the statement or the sign convention we're using is saying, if the algebraic sum of the forces is to the left of the section. So let's say there's a force going up here, and then there's another one down there, and maybe another one up there, another one down there, another one going down there, and then another one going up here. Okay, if you look at the forces, let's say this was drawn to scale, you can see that that's a big force, but that one is very big, even bigger than the first one, right? And then there's there's another one here, obviously, and then forces that are going down, you only have two, and it's a very small one, right? Okay, but the ones that are going up, you can see they're quite significant. So the chances are, what will happen here is that the algebraic sum of the forces to the left of the section, I need to rotate this. What's going to happen here is that the algebraic sum of the forces to the left of the section, they're going to go up. That's basically what's going to happen, right? So if you look at the algebraic sum of the forces, so you've said, okay, plus that, minus that, plus that, minus that, plus that, then if the algebraic sum of the forces to the left of the section go up, and we take this as positive shear. Remember, I'm taking the section to this point. So if the algebraic sum of the forces to the left of this being the section I'm highlighting is going up, that's taken as positive shear. So let's go back to the statement. What is the statement saying? Positive shear is when the algebraic sum of the forces to the left of a point or a section is upwards. Okay. So strictly speaking, okay, I just need to show you something now. Let me use my I want to show you something. Let me use my study notes, right? Your study notes, but I have copied because I want to show you something. So what I'm saying to you is this. All you need to do here is to just understand this part of the diagram. What is this part showing us? It's showing us that or obviously a positive shear if the algebraic sum of the forces to the left going up, it's taken as positive shear. So that's where we're cutting the beam, or that's where you're considering the section, you're taking a point or whatever the case is, right? If the algebraic sum of these forces, all these forces, right, going up, that's taken as positive shear. So this is basically what you need to understand. Now the rest is pure equilibrium. Okay, for example, if you have up here, then you have to have down there on the other side. That's pure equilibrium. Right. So now let's go to this page on Moodle. So on Moodle, I have uploaded a typical graph paper for you. I'm trying to open this graph paper. Please just bear with me, and this is taking time. Yeah, so I have uploaded this graph paper model. So when you draw shear force diagrams, okay, ideally you should use a graph paper. Okay, you need to draw these diagrams to a reasonable scale. At the end of the day, you need to, or someone else should be able to make sense of what you've drawn. Okay, so they need to be reasonably clear. They need to be labeled correctly. They need to be neat. So you need to look at your reactions and then decide on the scale you're going to adopt. So if I grab, let me get a graph paper. Please just give me one minute. I need to grab a graph paper. So this is the graph paper. So what are we going to do here is this. You're gonna, where is the problem we did last time? That I've got it somewhere here. Let's check to support reactions. Okay, this is the first problem we did. I've got, see, that's why I gave you that assignment, so that you can calculate the support reactions. I know exactly how to do it because we're gonna use that information, those reactions, to draw shear force diagrams, right? So this is the first question, question 1. And these are the support reactions at node A and node D. So now I need to decide on the scale. So what I can do is this. I'm going to say, right, got 84,5 on the left hand side. So what I can do now is this, right? Let me say, okay, if this is my zero line here, if this is my zero line here, and I'm taking this as 20, 40, 60, 80, 100, I'm fine, I'm sorted. Okay, if we're gonna be going downwards, then I'm still okay. Okay, 20, 40, 60, and the support reaction on this side is 65,5. So look, you don't want your drawing to be too small. You also don't want the drawing that's just too big. Right, so I'm going to then adopt this line as a zero line. Okay. So what are we drawing? We are drawing a shear force diagram. Sorry, this is S. My apologies about that. It's a shear force diagram. And the units for this, I just need to adjust. Okay, sorry. We have kilo Newton. These are the units we use in kilonewton. So we set 0 here, then we've got 20, 40, 60, 80, 100. This is just a guide, right? Because this is the first time we're doing it. And then this side we've got 20, 40, 60, 80, 100. We draw positive shear above the 0 line, negative shear below the 0 line. Okay, positive shear above the 0 line, negative shear below the 0 line. Any questions so far? Because I need to make sure that we all on the same. Any questions so far? Can we proceed?
Sorry, sir.
Yes, sir.
For tests and examinations, you want the shear force diagram drawn to scale.
I'll say to reasonable scale. You don't. If you have a ruler, obviously you can. It's easy for you to draw it to scale. But if you don't have a ruler, whatever you're giving me, you're gonna produce. It needs to be to reasonable proportion. Let me call it. Let me say it that way. Within reasonable proportion. So I need to be able to see on your diagram. If I need to be able to see a difference between a 10 kilonewton force effect and an 80 kilonewton force effect. Okay, it must be drawn to a reasonable proportion. If I give you a graph paper, yes, then you can just make your life easy. Then you can just draw it to scale.
I understand, sir. Thank you.
Okay, thanks. Right, let's continue. Positive shear we said above the 0 line, negative shear below the 0 line. Okay, and I said your diagram must not be too small or too big. Shear force diagram, units, kilonewton, and I said to you that K there is the small letter K and then capital letter N for kilonewton. Now let's look at the horizontal scale. So what is the length of this beam? How long is this beam? This beam is 10 meters. So how are we going to then decide on the horizontal scale? Okay, I'm gonna do it. So what is this? Okay, right. So what if we say 10, 20, 30, 40, 50? Okay, I think it's gonna work. So that's 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. Okay. Okay. So basically what I mean by that, this is in fact 10 meters. That's 1 meter, 2, 3, 4, etc. Right. So that's 1 meter, 2 meter, 3, 4, 5, 6, 7, 8, 9, 10 meters. Okay, the beam is 2 meters, not 100. Right. So I think it's going to fit in nicely here. The most important thing now. Let me open Paint. I don't have a stylus pen, so I'm going to have to try and actually do this using my mouse. So that's the beam. We have the a support reaction here of I said 84.5 kilonewton. That's the support reaction. Okay, so this is node E, okay, where you have your pin support. What are you going to do now is this. You're gonna go to node A. So this is node A. So at node A, you're going to look at the algebraic sum of the forces just to the left. There's nothing here, basically. To the left, there's no force, right? The side of node A, there is no force. The 84.5 kilonewton is applied directly at the node. So I'm saying this force, how do I highlight this reaction now? Okay, but anyway, this support here of 84.5 kilonewton, this support reaction is applied at the node. So what we're going to do now, you're gonna go just to the right of node A, just to the right of node A. The distance between node A and just to the right, that point, that section or the point we're considering is infinitesimally small. It is the smallest distance you can think of. So you go just to the right of node A. If you go just to the right of node A, what's gonna happen is this. So now you have, if you go just to the right of node A, now this is where we're taking the section. This is node A, and we have a vertical support here of 84.5 kilonewton. If you go just to the right of node A, right? So this is the free body diagram we have, and I said to you, this distance here is infinitesimally small. So think of any small number. I'm saying to you, the distance you see here is smaller than what the number you're thinking of, right? So now, what is the algebraic sum of the forces to the left of the section? Because this is a section. This, what you're looking at, this is a section. What is the algebraic sum of the forces to the left of the section? Only one force, 84.5. I know somebody's going to say, okay, but there is a UDL here just to the right. That UDL just to the right is so small because the distance you're considering is infinitesimally small. So that UDL is negligible. You're going to end up with 84.5 going up. So we've got 84.5 kilonewton going up. Now, if you go to your notes, you said algebraic sum of the forces going up to the left of the section, that's positive shear. Then now you're going to go to your graph paper and see. I think I lost the pen here. Now, I don't know what it is. Okay, yeah, I've got it. So now, this is node. Okay, that's node A. This is node A. At node A, we then start. We're gonna start with a vertical line of force of 84.5. Say it's somewhere there. Okay, so that's gonna be 84.5 kilonewton. So that's the force here. So what you can't do is this. Okay. We've got 84,5 and it's a plus. So we've got positive shear. Right. And then remember, this is a graphical communication of how your shear forces are in your beam. Okay, so we just need to do a graphical representation. So basically, you do it where there is a change in load, or there's a sudden change in load, so to say. You do at the point of interest, okay, where you might be interested to know what is the shear force at that particular point. Okay, so if you want to practice, you can do it every meter, but I'll do it from. In fact, what I'm going to do, I'm going to do it every meter. Okay, I was actually thinking of doing it at node A, left, right, B, left, right, C, left, right, D, left, right. But anyway, well, let's do it at 1 meter interval. Right, so 1 meter we're somewhere here. Okay, so that's the point now. That's the section we are looking at. What is the algebraic sum of the forces just to the left of the section? So we're saying the free body diagram now we have looks like this. So we have basically, in fact, we have a UDL. There's a UDL there, and then we have a support reaction. There's the support reaction. There's the support reaction there. We have already established that the support reaction is 84,5 kilonewton. We've established that. We know that the UDL is 10 kilonewton per meter. Yeah, that's 10 kilonewton per meter. And then we're saying the section under consideration is there. This distance, there is a line with 2 arrows here. Okay, anyway, sorry, I'm gonna make a plan. Okay, sorry, that's where we're cutting this section. And then I'm saying to you that distance there is 1 meter. So this is your free body diagram. So currently we're sitting at 84,5. So we're gonna say, right, plus 84,5 minus. Okay, plus 84,5 minus what? So we need to minus that load there, you know, that 10 kilonewton per meter over a distance of 1 meters. Okay, so it's 10 kilonewton per meter times 1 meter, then you get 10, then so it's 84,5 minus 10. Okay, then you get 74,5. So on our graph paper, where is 74,5? So on our graph paper, 74,5 is, that's 1 meter, is somewhere there. Okay, so that's 74,5. And then we're gonna yes, I'm listening, sir. Yes, sir. Who's talking?
Explain that.
Oh, okay, my apologies. I thought somebody was talking. Right, so I don't know, maybe I'm hearing voices. Right, so let's continue. Okay, so we've done this one. So we've worked out the shear at this point. We know it is 74.5. There you go. Now the next point of interest. Next point of interest is node B. Okay. At node B, we're going to consider forces to the left and the forces to the right. That's what we're going to investigate if we do B left. So we still have plus 84.5. Still have plus 84.5 and then minus 10 times 2. B left excludes the point load of 30 kilonewton. And then B right will then include the point load of 30 kilonewton. So we're currently doing B left. So the free body diagram for B left looks like this. Sorry, I think I'm running out of images. I'm not wasting paper here now, so I can just delete this as much as I want. So, right, so where are we? We're saying that's the support reaction there. And then we have the UDL here. I'm saying, okay, that the support reaction is 84.5 kilonewton, and then the UDL is still 10 kilonewton per meter. And then where is node B? Node B is here. That is node B. Node this is node B. This distance that distance is 1,999999999. That's the distance. Okay. Why I'm gonna write it like this? It's 1,99999. I'm gonna write it like this is because basically we're just looking just to the left of a node B. So that distance there now is the one that I'm gonna say to you, it is infinitesimally small. Okay, so in fact, sorry, this number is still continuing, right? Right. So now we can take it as 2 meters. Okay, so when you do the actual calculation, what you're going to do now for this is this side. You're gonna say plus. You're gonna say plus 84.5 minus 10 times 2. That's how you're gonna do it. You're gonna write it as 1,2. You're not gonna write it as 1,99999. So you're gonna write it like this. Then you get 64.5. So question is where 64.5? 64.5. In fact, I made a small mistake here. So I need to write this somewhere here. My apologies about that. And then this one is going to be 64.5. Okay, right now, where is the question? At node B, you go just to the left of node B. The free body diagram you have now looks like this. So you've got the support reaction of 84.5 kilonewton. Then we have this segment now. Okay. And over and above that, we have a, how do I draw this? Okay, so that's, I need to use this one. Then we have the point load there of, sorry, I forgot the point load, of 30 kilonewton. So there's 30 kilonewton. Where is node B now? Okay, node B is here. Okay, that's where node is. Let me just maybe and I need to elaborate this, make it more like significant slightly, right? So when you do B right, this is node B. Now when you do B right, you will then include the 30 kilonewton. So what you then need to do is this, plus 84.5 minus, why minus? Right, there's a UDL. Where is that UDL? This one. Where are we? B, right, just to the right of node B. So it's 10 times minus 10 times 2, then minus 30 kilonewton. Then you get 34.5. So on your graph paper now, where is 34.5? So 34.5 is 34.5 is somewhere there. So far what we can do is we can just join these 2 points. So it's supposed to be a straight line. You'll have to forgive me for this. You have to join those points now, right? So here we have 34.5. Right. So what you're gonna do when you do this at home, then you're gonna, when you do a revision, rather, what you're going to do, you're going to do it every meter. I'm seriously running out of time, so I need to go straight to node C. At node C, I'm going to look at C left, just to the left of node C. So if we do just to the left of node C, so you can also grab your calculator. If we look at just to the left of node C, we've got plus 84.5, then minus that UTL, okay, goes over 7 meters, so minus 10 times 7, then minus the 30 there, and then minus, okay, if you just to the left, you don't include 50. My apologies. Right, so you get, now I'm getting minus 15.5. So this is 1 meter, 2 meter, 3 meter, 4, 5, 6, 7 meters is there. That's 20 there, 15 should be exactly there, right? So then you just need to join these 2 points, right? And then you need to do C right. C right will then include the 50 kilonewton point load. So currently I am sitting at, minus 15.5, and then now if you include that point load of 50, then it's going to be minus 15,5 minus 50. Then you can see that now you need to go further down to 60 to minus 65,5. Right, so right, so there you go. And then okay, right, if you go to node D left, okay, if you go to node D left, you will realize that you're still dealing with the same forces. Inside inverted commas, the algebraic sum of the forces to the left. Okay, hence your shear will be constant. It stays constant, right? And then you then have 65,5. Let me just show you on my screen here, which is exactly your support reaction, which we calculated there. So you're sitting at minus 65,5. Now, when you include the support reaction, so you've got plus 65,5, and then it tells us that, as I told you, that the shear is constant. You can check it every meter. There you notice that, and then it goes back to 0. You have to finish at 0. Okay, if you don't finish at 0, then it's obviously a mistake somewhere. Right, so if I ask for a fully annotated shear force diagram, so you can just you don't really have to show that 74,5. I just did it because at that time we were doing it every meter. So you need to show that 84,5, you get a mark for it. You need to show that 64,5, you get a mark for it, or half mark. 34,5 needs to be shown. You need to show this one. This one was 15,5, I think. Apologies, I forgot to write it down. And then this one 65,5, you need to show it. You get a mark for that. And then here is 65,5, you need to show that. And then it goes back to a 0. So you need to tell us that this is the shear force diagram and the units you're using kilonewton, and then you need to show us which side is negative shear, and you need to show us which side is positive shear. And as far as these diagrams are concerned, if it's half mark, then it's a tick with that line there. It's like half tick. So that's how we actually we show it, right? So then it's obviously a mark or two for getting the whole shape correctly, the entire shape. Sometimes we do it like that. So if the entire shape is correct, then you get that the 2 marks. Right, so fully annotated, you show those values at critical points, points of interest, where we have discontinuous lines. We have discontinuity, and next time we'll talk about discontinuity lines, where we have a sudden change in load. For example, here from 64,5 to 34,5, there's a sudden change in load as a result of this point load of 30 kilonewton. So you need to indicate those values, right? So let's look at the next one. From there to there, again, you need to do that. And then if it's a straight line, or this line is parallel to your axis, then it needs to be shown as exactly parallel. So if you like, you can just do this, show it by just showing those 2 arrows. That fine, it shows that 2 lines are parallel. And then what else I missed out here? I just need to make sure that yeah. So the last thing we need to talk about is this point here. So is this point? This is where your shear force equals to 0, right? So So today, all we need to do is to calculate, determine the position. So to do that, what we're going to do is this. So I'm going to just draw some construction lines here so that it's easy for me to explain. And then we're going to say, right, the distance from node 2 to where the shear force is 0. Let's make the distance x. And then what is the height from the distance from 34.5 to what 15.5. So what is that distance? So that distance, you need to work it out. I'm going to put it as y, but you can actually work out that distance. And what is the distance from node 2 to 7? Okay, also that distance you can work it out quite easily. Let me call it z. And then all you need to do now is to use apply similar triangles. So in this case, basically, you can simply say y over z equals to 34.5 over x. Right, then you solve for x. Okay, you know what y is, you know what z is. All you really need to work out here is x. And then once you've worked out x, then what you need to do is to go back to the diagram and make sure that it is indicated clearly. Make sure you indicate clearly that a position, so everyone will know that from node 2 to the 0 shear, it is x meters. Okay, and then right, that will be your shear force diagram. Students, there is obviously a problem here. I forgot to explain it last time. I'm currently using MS Teams, and so far we've gone close to 2 hours now. It's 12:46. So now what is happening? I'm going to send a link on Moodle. Okay, a link for this video on Moodle. It is very important that you watch. Okay, on my side, I'm begging to download MS Team videos that I think more than 2 hours. That is why even last time I said I'm gonna put the video on Moodle, but it ended up being a link. So you just need to make sure that you find a way to download it as soon as possible, or you watch it as soon as possible. If for whatever reason you miss the lecture. Because what's going to happen, I think, I'm just speculating now, you'll probably find that maybe after, say, 5 or 6 sessions, you may not be able to maybe get those lessons. So it's very important that you do it as soon as possible. And if you could please pass the message to other students. Right, but we're going to continue. So I just wanted to make sure I don't forget that. And then the next one that we need to...
Sorry, sir.
Yes, sir, I'm listening.
Before you continue, I see that you mentioned Moodle, and a lot of the teachers are mentioning Moodle.
Yeah.
Have you inquired with regards to the Moodle problem? Because I sent Mrs. Steele an email with regards to the Moodle problem, and she forwarded it to the ITS people, and they did not respond. So now this matter is becoming increasingly alarming, because there are other subjects which I can't access on Moodle, and every teacher is saying Moodle this, Moodle this, Moodle this. So, and I don't understand sincerely what's happening.
Okay, I'm very sorry about that. As far as I know, I didn't know that maybe there is possibly an issue with the model in terms of some students maybe logging into model. We've been told, I think this is the message. Basically, all lecturers have been given that we just need to tell the students log into model so that they can be automatically enrolled on MS Teams. So if I look, for example, here on my module, okay, this is the module we currently doing, right? So immediately I can see, for example, that the student Bayat has never logged into model, and I can see clearly I think hasn't. And in fact, yesterday I actually selected these students and I sent them a message, which I think it's actually an email, not an SMS, a message requesting them to log into model. So in your case, can I just check something here if you don't mind? Sorry, who's
Yes,
speaking? Makazi.
Yes, sir.
So in your case, let me see if okay, to make life easy, let's go by surname.
I can give you the student number and you search the student number.
Okay, no, I think let me just try and actually do this. So I'll tell you why I'm not a computer person, so I don't want to put myself in this corner. But you sure you fully registered? You registered?
Sir, I've registered for every subject. And so with regards to saying that that once you log into Moodle, you should be automatically added. With regards to me, the only subject I have like three subjects on Moodle, and I've logged into the civil engineering material class, and the Moodle system added me for that class. But with regards to the transport A, it has not added me. And when you relay the message, the lectures just say that we have been informed that you must log into Moodle, and then it just becomes a frustrating process.
Okay, no, I hear Menier. I hear you, but can I just ask you a question? Are you aware that you need to log into every subject to register for on Moodle?
I can't hear, sir. Can you repeat?
You need to log into each and every subject you are registered for, on Moodle for this current semester. Have you done that, or you just logged into Moodle only? Did you?
I've tried. I've logged into the subjects which I can access, and I've downloaded some of the material. But for example, with regards to your class, in order for you to add me on Microsoft Teams, I had to tell you personally.
Yeah.
Because the Moodle thing did not work.
Oh,
yes.
okay.
So I'm stuck, and I don't understand what's the next process as to solving this problem.
Oh, okay. Well, what I'm going to do is I'm going to send an email to Dr. Pinar. He's the person who helps us with the model for the faculty of in the faculty of engineering. I'm going to ask him to, but I can only do it for this subject. I'm going to ask him to take the list from the ITS and bulk enroll all students, and then you can see if that's going to help. I don't know. So just do the re-enrollment of all students.
Yes, please try, and thank you for the assistance.
Oh, okay, but sorry, Makazi, what I'm trying to I don't see your surname here.
Yes, I'm not on Moodle with regards to this class.
Oh, okay. Okay, but okay, you are on MS Teams just because I manually enrolled you on MS Teams.
Yes, sir.
Oh, okay. You didn't use the link to. You did not use the link I sent via email yesterday to log on to this class, am I right?
No, I didn't use the link, sir.
Oh, you went straight to MS Teams.
Yes, sir.
Okay, I just need to make sure that I get your can I get your email address then so that
No, yes, it's
your student number is
2171
yes.
47
Oh yeah, it's speaking that.
66. Yes, then.
Okay, now what I'll do is I'll send an email to Dr. Pinar. I'm gonna ask him to re-enroll all students. Okay, maybe what if it works, obviously I'm gonna copy on the email, and then if it works, then maybe you can just ask lecturers for the subject to do the same if it works.
Okay, so I'll surely try, sir. Thank you.
Okay. Right. Students, now the last part will only take 5 minutes, right? And then the rest you need to basically do it as part of assignment 2, obviously, which I have uploaded on MS Teams. Now I want to show you this one, question 2. Right. When you do question 2, I'm going to do it now from right to left. I know it's a little bit awkward, but I need to show you something, right? So if we go to, okay, let's maybe first decide on the scale. So I'm doing it now from right to left. Okay, then we still have that there. And then I'm going to say, okay, that's the 0 line there. Okay, this is the shear force diagram, units kilonewton. Okay, how long is this beam? Okay, so it will definitely fit. Okay, so let's say this is that's so you will decide on the scale you want to use. I'm just doing it my way here, right? So there is 15 kilonewton. There is 15 kilonewton. So let me show you something. All right. Let me a new page. Don't save this one. We have at the tip of the cantilever. At the tip of the cantilever, we have a point load of 15 kilonewton. Okay, right. And this is where the node is. The load is actually applied at the node. Okay, this one, right, at node E. So this is where node E is. Okay, I just need to undo this. This is where node E is. Okay, right, there's node E. Now, we're going to go just to the left of node E. This distance, okay, this distance here is the one that is infinitesimally small now, right? So if I go just to the left of node E, so what we have there, strictly speaking, is a point load of 15 kilonewton. So
excuse me.
yeah, yes, I'm listening. Sir. Yes.
I
yes, I'm listening.
I don't want to sound rude or anything. We are going to have another class at once, so I was thinking that we could just.
Oh, okay. No, it's fine. You have another class. That's okay. So, what we'll do is, yeah, I will. I think you can continue with assignment 2, but then you have to start from the left-hand side for all the problems. Otherwise, it might cause a bit of a problem. So I just wanted to explain just a small short concept, but I understand and I realize that you have another class. So I will then see you on Friday to do the corrections for the assignment you're going to submit by this day latest. Okay. Okay, students, can we call it a day?
Thank you, sir.
Okay, thanks, Jeza.